Welcome to Shanti-Peace for Mathematics. In the previous videos, we have learned about what is a differentiable function for two variables. So let us recall, if you have a given a function which is defined over D to R, where D is a subset of R square, and if x0, y0 is a point in D, if you want to say that this f is differentiable at point x0, y0, then it has to be satisfy this condition, that is x0 plus h y0 plus k equal to f of x0 comma y0 plus h into fx at x0 y0 plus k into fy at x0 y0 plus h into epsilon 1 hk, which are the error term, and k into epsilon 2 hk, where epsilon 1 and epsilon 2, they are the functions of h and k, will tends to 0 as hk tends to 0. Also, we have seen that if f is differentiable, which implies that fx and fy are exist, this will guarantee that if f is differentiable, fx and fy are exist. That means a function is differentiable, then the partial derivatives are always exist. But we have seen that the converse of this result is not true. That means if fx and fy are exist, will it not implies that f is differentiable? That also we have seen by an example. Here we are trying to discuss, if you add some condition with the fx and fy, then will it be f become differentiable, and that is nothing but the sufficient condition for differentiability. So what is the sufficient condition for differentiability? We will state it as a theorem which state that let f be a function which is defined on D, which is a subset of R square to R, and x0 y point in D, such that the following holds. The first one is fy is exist at all point in the neighborhood of x0 y0, and the second one fx is continuous at x0 y0. Then f is differentiable at x0 y0. Now, as we have discussed earlier that f is differentiable, that will implies that fx and fy are exist. The converse is not true. So what we are doing here, we are making one extra condition here to make the converse exist, that we are adding one more condition here, that is fy is continuous. If fy is continuous, then f will become differentiable. So this statement is also stated in this manner: both partial derivatives are exist and both of them are continuous, then f is differentiable. Or you can make it the statement in this manner, that fx is exist and fy is continuous, then f is differentiable. So this statement is stated in three ways. I am repeating again. The first statement we can write, this is written here, which is in the similar form. The second one, we can say that instead of fx and fy, we just write down both partial derivatives are exist at the point in the neighborhood and both partial derivatives are continuous, then f is differentiable. Or you may state in the third manner is, instead of fy you just write down fx, and here you will write down fy. So instead of this you write fy, and instead of this if you write fx, then also you can state this same manner. But right now I am proving for this only, so I am just removing that thing and stating that fy exists and fx is continuous at that point. So let us discuss the proof for this theorem, and this is the sufficient condition for differentiability. Given that fy is exist in the neighborhood, so that means this limit, what do you mean by fy by definition, at point x0 y0, that says that k tends to 0, f of x0 y0 plus k minus f of x0 y0 upon k is equal to fy at x0 y0. Now if you write down this is in the another manner, that we can write as x0 y0 plus k minus f of x0 y0 upon k. So I am not writing now limit. So if you remove this limit, there will be error term is added on this side. So it is fy at x0 y0 plus some error term. So it is, let's say, xi xk. So ultimately what we can write this is as, therefore f of x0 y0 plus k minus f of x0 y0 equal to fy at x0 y0 plus k into fy at x0 y0 plus k into xi. So if you multiply both side by k, we'll have this. So let's say this equation is 1. I'm calling this equation as 1. Now also given that fx is continuous at x0 y0, we can say that fx is exists in the neighborhood of x0 y0. So we can say this statement that f is differentiable with respect to x in the interval x0 to x0 plus h. So what is this? It is actually fx. Fx is nothing but the partial derivative of f with respect to x. So that means we can say that if f is partial differentiation is exists, that means f is differentiable with respect to x, keeping y constant. So that we can state. So what is this statement now? F is continuous in this neighborhood, f is differentiable in this neighborhood x0 to x0 plus h, and then what is this two statement satisfying? This two statement satisfying the hypothesis for Lagrange mean value theorem. So let us recall what is Lagrange mean value theorem that we have known as a LMVT. So let us recall that statement. So LMVT states that f is a function which is defined from a to a plus h to r close interval. Then first statement is f is continuous on close interval a to a plus h. Second statement, f is differentiable on open interval a to a plus h. Then there exists some theta in 0 1 such that f of a plus h minus f of a upon h is equal to f dash of a plus theta h. This was the statement of LMVT, or I can say there are different statements. Let's say that f of b minus f of a upon b minus a is equal to f dash of c, but that statement we have equivalent to write down in this statement. So by recalling this LMVT, because I required this theorem to use here, fx is exists, that means it is differentiable in this neighborhood 0 to x0 plus h, and it is also continuous in that neighborhood. So that means what we can say by LMVT. So using LMVT, we say that there exists some theta which is in the interval 0 to 1 such that f of x0 plus h comma y0 plus k minus f of x0 y0 plus k upon h is equal to f dash, but that derivative is with respect to x, so that's why we are writing fx at x0 plus theta h into y0 plus k. So what we are saying, this y0 plus k, we make it fixed variable, we are just changing in x. So that is the x0 plus h to x0, and that's why it is x0 plus theta h. So in this theorem we have, instead of a we have x0, so we'll have this. Now if I take the limit in this as h tends to 0, so taking limit h tends to 0, what we get, limit of this h tends to 0, f of x0 plus h y0 plus k minus f of x0 y0 plus k upon h is equal to, on this side, limit h tends to 0 fx x0 plus theta h comma y0 plus k. Also using the argument that fx is continuous at x0 y0, so we can say that limit of fx at x0 plus theta h y0 plus k as hk tends to 0 0 will be fx at 0 x0 y0. Due to continuity we can say this, because you know that if f is continuous, limit of f of xy is nothing but the f of x0 y0 as xy tends to x0 y0. But here we have hk tends to 0 0, so that's limit I can take inside, so we'll have this one. Now again, if I not writing this limit, then what we'll have is we can add some error term here, so that we can write as fx at x0 plus theta h y0 plus k is equal to fx at x0 y0 plus some error term which is function of hk will be there, where obviously this phi of hk will tends to 0 as hk tends to 0 0. That is the error term we have. Now we'll call it, this is as a equation 3 and this one will be equation 2. So using this value of 3 into what we get will gives you can see that here it is x0 plus h y0 plus k x0 y0 plus k. So it is fx at x0 plus h y0 plus k minus f at x0 y0 plus k upon h is equal to fx at x0 y0 plus phi of hk, where phi tends to 0 as hk tends to 0. That can be written as x0 plus h y0 plus k minus x0 y0 plus k equal to h into fx at x0 y0 plus h into phi of hk. If I call this is as statement number 4, use this value of 4 in 1. So let us see that what is the equation 1. Equation 1 is this, that is x0 comma y0 plus k minus f of x0 y0. Now what we'll do is we'll start with this. We'll start with x0 plus h y0 plus k minus f x0 y0. So I'm starting with this side, I'm adding these terms, that is x0 plus h y0 plus k as it is. So I'm adding this term and subtracting that term, that is x0 y0 plus k plus f of x0 y0 plus k minus f of x0 y0. So this I can write as this value because of equation 4, that is h of fx x0 y0 plus h phi of hk. Now value of this we can write from the equation 1. The equation 1 is we have written here, that you can see that f at x0 y0 plus k f of x0 y0, which can be written in this form. So that's why we can write this is as k into fy at x0 y0 plus k into xi of k, where you should notice that this phi of hk is tends to 0 as hk tends to 0 and xi is also tends to 0 as k tends to 0. That's in the equation 1 we have. So this xi is an error term, that is tends to 0, and This phi is also tends to 0, as it is also an error term. So finally what we got is f of x0 plus h y0 plus k minus f of x0 y0, if I take it on the other side, plus h into fx at x0 y0 plus k into fy at x0 y0 plus h into phi of hk plus k into xi of k, where phi and xi tends to 0 as hk tends to 0. So that proves that f is differentiable at point x0 y0. So what I will suggest you, if you have not understood this theorem yet, please repeat the video and sit down with the note and pad and write down step by step. Definitely you will understand that. So with that note, we will say that the converse of this result is not true. That means that what is the statement we have here is, if fx and fy are exist and fx and fy are continuous, then f is differentiable. This is the theorem we have proved just now. The converse of this statement is not true. That means if f is differentiable, we definitely say that fx and fy are continuous. That we have discussed in my previous video. But if f is differentiable, we cannot say that fx and fy are continuous. So we need to give the counter example for that to disprove the converse of this result. So for that I am giving you example here. So consider or define a function fxy as this way, that is x square sine 1 upon x plus y square sine 1 upon y. This is defined if x is non-zero, y is non-zero. If x is non-zero, then it will define as x square sine 1 upon x. Y square sine 1 upon x is defined when y is non-zero, and 0 if x and y both of them are 0. So this function is defined over r square, and we have to prove that f is differentiable at 0 0, and second one, fx and fy are not continuous at 0 0. So let us calculate what is fx at 0 0 first. So as per the definition of fx, h tends to 0, 0 plus h comma 0 minus f of 0 0 upon h. So this is limit h tends to 0, which will be f h comma 0 minus fx at 0 0 upon h. Now what is f of h comma 0? F of h comma 0, that means x is non-zero. That means this is the function definition. So that will gives you limit of h tends to 0, h square sine 1 upon h, and f of 0 0, both points are 0, so that's why it has a 0 value. So this will gives you 0 upon h, and this h is cancelled out, so we'll have limit of h into sine 1 upon h. As I have given you this argument also before, that is mod of sine 1 upon h, you may write as less than or equal to mod h. So therefore the limit h tends to 0, mod of sine 1 upon h will be limit of mod h as h tends to 0, which is 0. So by sandwich theorem, what we can say is limit of h sine 1 upon h will be 0 as h tends to 0. So therefore fx at 0 0 will be 0. Same way fy at 0 0 will write as limit of f 0 comma 0 plus k minus f of 0 0 upon k as k tends to 0, which will gives you limit k tends to 0. This is 0 comma k minus f of 0 0. Here this will tells you that y is non-zero. So for y is non-zero, it has a function y square sine 1 upon y. So due to that, this will gives you limit k tends to 0, k square sine 1 upon k, and f of 0 is already 0 upon k. So that will gives you limit k tends to 0, k upon sine 1 upon k, and k into sine 1 upon k will be 0, the same argument as I given above. So that's why we can say that fy at 0 0 will also 0. Now what will be the fx at any point? The first one, fx at 0 0 is 0, that we have calculated. So fy is 0 0, then we have calculated it is 0. What will happen if it is x is non-zero and y is also non-zero? In this situation, that means in this situation, what is your fx? Fx is nothing but the partial derivative of this with respect to x, because for x is non-zero, y is non-zero, the function is defined in this manner. So the derivative of this with respect to x will gives you 2x, because that function is x square sine 1 upon x, y square sine 1 upon y. So that will gives you 2x sine 1 upon x minus x square, as it is derivative of sine is cos 1 upon x, and the derivative of 1 upon x is minus 1 upon x square, and this x square will get cancelled out. So it will have 2x sine 1 upon x cos 1 upon x. And what is if x is 0 and y is non-zero? X is 0 and y is non-zero, that means this will have this value y square sine 1 upon x. The derivative of this with respect to x will be 0. So that's why we have fx at 0, x 0 and y non-zero will be 0. So finally, what is fx at any point xy will have this. Same way, fy at any point xy can be written, if x is non-zero, y is non-zero, then it will be 2y sine 1 upon y minus cos y, in the same manner. Because x is non-zero, y is non-zero, the function is this x square sine 1 upon x. So the derivative of this quantity will become 0, and this will gives you the product rule. Using the product rule, we'll have this 0 if x is non-zero and y is 0. If x is non-zero, y is 0, then it will become 0. 0 if both of them are 0. Okay, so that means we can say that fx and fy are exist everywhere. Now we have to prove that, according to our example, we have to prove that fx and fy are not continuous at 0 0. So to do this, let us see what is the limit. Limit as xy tends to 0 0, fx at xy will be limit xy tends to 0 0. Fx at xy is, as you know, that it is 2 times x into sine 1 upon x minus cos 1 upon. So it is 2 times x sine 1 upon x minus cos 1 upon x. Now this will be 0, because we have already discussed that x into sine 1 upon x, as x tends to 0, this will be 0. But what about this? It will be infinitive, because cos infinity will have. So this is does not exist. So the limit is not exist. So therefore fx is not continuous at 0 0. Similar manner, we can say that the limit of fy, which is this, is also does not exist, because here is also cos 1 upon y is there. So that's why we can say that similarly fy is not continuous at 0 0. Now we shall show that f is differentiable at 0 0. So it is enough to prove that. What is the proof is necessary and sufficient condition for differentiability? If you remember of my previous video, that tells you that hk tends to 0 0, x0 plus h y0 plus k minus f of x0 y0 minus h fx at x0 y0 minus k fy at x0 y0 upon square root of h square k square equal to 0. If we prove this, then we are through. So what is this? Let us start with that side, that is limit hk tends to 0 0. The first one is x0 is 0, y0 is 0, so that is hk minus f of 0 0 minus h into fx at 0 0 minus k into fy at 0 0 upon square root of h square plus k square. Now what is f of hk? Just recall the definition of f, that is x square sine 1 upon x, y square sine 1 upon y. So that's why it is equal to limit hk tends to 0 0 h square sine 1 upon h plus k square sine 1 upon k minus f0 0 we have 0, h into fx at 0 0 we have calculated it is 0, minus k fy at 0 0 also we have calculated at 0 upon h square plus k square. Now we have this. So finally we'll have limit hk tends to 0 0 h square into sine 1 upon h k square into sine 1 upon k upon square root of h square plus k square. We have to show that this is 0. So for that I am starting with, for every given epsilon greater than 0 there exists a delta greater than 0 such that, so we shall show this, we shall show that h square 1 upon sine 1 upon h plus k square sine 1 upon k upon h square plus k square minus 0 less than epsilon. This we need to prove. So what is this? Is actually I am starting with this side, that is mod of h square sine 1 upon h plus k square sine 1 upon k upon h square plus k square, that by triangle inequality we can write as h square upon square root of h square plus k square mod of sine 1 upon h plus k square upon square root of h square plus k square mod of sine 1 upon k. But sine function is always less than or equal to 1. So this is h square plus k square upon square root of h square plus k square. But this will be the less than or equal to square root of h square plus k square. And you know that in the neighborhood, that is h less than delta and k less than delta, will implies h square plus k square is less than 2 delta square. So that is square root of h square plus k square will less than square root of 2 delta. So this is square root of 2 delta. If you want this is less than epsilon, then your delta should be less than epsilon upon square root of 2. So that proves that f is differentiable at point 0 0 because this limit will be 0. So that's why this is true. So f is differentiable. So that is the converse of the sufficient condition, that if f is differentiable, then it does not implies that fx and fy are continuous. Definitely we can say that f is differentiable, fx and fy are exist, but we cannot say they are continuous. So with that note, I am giving you some exercise here, that is, if I have a function gives you, that is x square y square upon x cube y cube, where xy is non-zero, 0 if xy is 0, prove that fx at 0 0 and fy at 0 0 are exist, f is continuous and f is not differentiable. So with this example I am stopping here. If you have liked this video, please press the like button. If you have any comments, suggestions or questions, please drop down in a comment box below. Thank you. Bye bye. Sayonara.